Hello everyone, this is Anton Glinkin from CDT, and today we'll be talking about ZPlanner in application for superior accuracy in PCB design. Something that we will be discussing today. It is stackup planning challenges, mastering impedance planning with ZPlanner, optimizing material selection for perfect impedance control, streamlining design verification, reducing iterations, collaborate with fabricators, and achieving a robust and high-performance PCB design. As usual, at first I will give you a little bit of marketing information to understand the problematics we are talking, and then we will switch to practical stuff and I will show you something useful. So let's talk about how ZPlanner acts as the ultimate connector between design and manufacturing. The big challenge in PCB design, the biggest one, is ensure that what you simulate is exactly what you will get in the result, what gets produced. Traditionally, this means endless back and forth exchange of information with fabrication house about impedances, about stackup details, materials, etc. ZPlanner Enterprise eliminates this complexity and it seamlessly links your design, your signal integrity requirements, and your OEM specifications directly to the manufacturing process. This means your stackup proposal matches your design intent, and you simulate the real-world build, and your planned impedance and material choices are precisely what fabricator delivers. In short, ZPlanner automates coordination across the design and fabrication and giving you confidence that your PCB will be meeting performance targets without additional iterations or problems. So let's look why planning your PCB stackup can be such a problem today. As you can see, it's often bumpy road with many different steps and people involved. We have hardware engineers, we have materials expert, PCB designers, signal integrity engineers, and manufacturing teams that working on the same project. What is the problem? Everyone often creates the stackup, recreates the stackup in their own way, in their own tools, with their own methods. Think about it like this. Our stackup tool is in the middle, but it is surrounded by many separate tools like those for SI, CAD, design checks, and even very simple spreadsheets. Each of these can become its own little island of information. This separation means that there is no single clear version of the truth. Without one complete stackup plan that goes smoothly from design to the factory, teams often work with old or missing information. This leads to expensive respins, frustrating delays, and unexpected problems that can stop projects in their tracks. Plus, manually typing in stackup details into design software is slow and open door to more mistakes. These are not small issues, they pretty major, I would say. They show us why bringing everything together is so important. What we really need is a system where all parts of the design, like hardware, software, and physical details, work together perfectly with design and analysis tool. And that's exactly what ZPlanner does. It brings everything together, making stackup planning simple and clear. It stops duplicate work, cuts down on errors, and makes sure everyone is using the same correct information. If you send your stackup specification into 3 different fabricators, you would surprisingly receive 3 slightly different finished products. But those slight differences can make or break the performance of your high-speed PCB design. Each fab have own assumptions about cuprum and copper, and using only 1 GHz for calculation. On the right side, you see a loss curve for 3 supposedly identical boards from fabricators. However, analysis shows very different characteristics at 10 GHz. The answer to the why is that they were using different copper roughnesses and different oxide alternative treatments and many other small assumptions they've done to fit your requirements. On the 1 GHz, these differences would be almost zero, but on 10 GHz, on multi-gigahertz range, it will be significant effect. One of the biggest challenges companies have regarding stackup planning is communication and collaboration with PCB fabricators. Now that we've seen these challenges, let's look how ZPlanner solved them. It gives you intuitive, integrated environment for all stakeholders, from designers to fabricators. Everything is built around a single source of truth, that our specification file. So mechanical, signal, and power integrity requirements are defined and validated against the actual fabricator stackups. Workflow covers every stage, from initial dielectric and impedance planning through the VIA and loss cost analysis to stackup approval and signal integrity expert. And with automated validation available in the zPlanner, you can ensure compliances without manual checks. In short, zPlanner streamlines definition, validation, and implementation, making collaboration faster, more accurate, and less error-prone. So often, stackup is used for signal integrity simulation is not the same that we will have after the fabrication. Changes may be made by layer heights and trace width. Materials may be used, and they may have specific values for DK and DF. Copper roughnesses will be associated with specific cores and foils. Prepreg on outer high-speed layers often has greater roughness on the foils than the cores. And what does it mean? How you can take this in consideration? If your simulations were not based on electrical characteristic of actual materials, then accuracy is very, very questionable. How we can fix this? zPlanner allows you to collaborate with fabricators. It can compare up to 4 stackups at a time, and it can save substantial time. There are 24 stackup specific DFM analysis that gives you assurance about manufacturability of this specific design. Also, it interfaces with PCB fabricators. It supports ODB++, IPC 2581. You have support of many other stackup files. And you also can provide this stackup inside the hyperlinks, our main tool for signal integrity. The whole idea of using zPlanner is part of Siemens paradigm, left shift. What does it mean? That all checks, in our case this is stackup verification and post-layout analysis, should be performed as early as possible. On the timeline, it will be left. That's why it's called left shift. So you can focus on stackup design changes on early stage to eliminate more costly design changes after. First thing that I already told you about a couple of years ago, it is tracking copper roughness. Deli sürüsüne çobanlık. So what is copper roughness? Why it is different? What all this abbreviation VSP VLP, HVLP, array RZ does mean? Let's start from the very basics. Electrodeposited copper foil is manufactured through the deposition of copper ions onto the cathode drum via electrolysis process. In practice, the foil is produced through the continuous rotation of the drum and simultaneous winding of the copper foil as it released on the drum surface. Drum speed controls the foil thickness, and it actually gives this different characteristic to our foil. One side would be shiny, and second will be matte. Matte side typically has different roughness than the drum side. But what is surface roughness? How is calculated? How to understand it? The most frequently specified roughness parameters are array and RZ. Array means average roughness average. It is typically used in the United States, while RZ, or mean roughness depth, is commonly used internationally. Array is defined as the average variation of the roughness profile from the mean line. In mathematical terms, this is integral of the absolute value of the roughness profile divided by profile length. Because of this averaging, the array value is lower than the actual height of the roughness variations. To calculate RZ, the roughness profile is divided into 5 equal lengths. The height difference between the highest and the lowest point in each of the 5 sections is known as the total roughness, or RT for that section. RZ is the average of the 5 RT values. The calculated RZ value is approximately the height of the most severe roughness variations. So, every material that you will use will have some definition, HTA, RTF, and so on. The problem is there are no firm standards for designating copper foil grades or roughnesses. There are several generic designations, but each copper supplier uses these terms indifferently. There is no progress at this moment for solid roughness standard. The only reliable way to control copper roughness today is to find out what the laminate manufacturers offer based on foil name, copper roughness and cost, simulate it to make sure that it will meet your insertion loss goals, and include this into your stackup specifications. As I said, we have two sides of copper. Core side is what most people think of when selecting copper foils. Knowing the prepreg side is important, but more challenging means rougher surface, stronger bond. But it also affects our impedance. Prepreg side is textured by the copper foil maker, plus PCB fabricator applies the anoxide coating on the top and side surfaces to maintain bond strength. Laminate side is textured by the copper foil maker who supplies the laminate vendor. So they will have different parameters. What is oxide? You can see it on screen. It is non-proprietary reduced black oxide. But there are also oxide alternatives. There is so-called McDermid multi-bond, Anthon alpha prep, McDermid multi-bond, and so on. And all of them have their own parameters. Proprietary products are technically oxide alternatives rather than true oxides. They texturize the copper surface rather than forming an oxide layer. True black oxide builds cuprum O, oxide of the copper, crystal structure up from the copper surface. It is non-conductive, and that's why it carries no skin current. The others edge down into the cuprum surface, thus texturing the copper itself, and so they do affect skin current. So you already see the difference. Skin current or skin effect is quite a big thing in our applications. So what is more important? What is more affecting our process? Is it base copper foil selection or process treatments? You need to understand that the major differences are due to the foil type. We can compare them with the mountains. The difference in the height of the mountains could be quite huge and will be affecting much more. And minor differences is due to the process treatment, like trees and hills. It is difference, but it's quite small difference in comparison to mountains. This is example how different roughnesses and oxides affecting same signal. You can see it that the roughest material gives you highest loss on standard foil and CZ 8100, but the smoothest foil gives you the lowest loss, and it's affected by using HVLP and black oxide. What is these abbreviations? I've made a small spreadsheet for you to understand. LP stands for low profile. VLP is very low profile and HVLP is hyper very low profile. So the more letters in this abbreviation and the longer it is, if it's scary, it is very smooth, let's say this. Since there are no unity in the manufacturer's standardization, you can take this as a reference to understand the limitations. The evolution of copper foils for high-speed applications. Before, back in times, up to 2003, laminate manufacturers had the rougher mud side on the copper facing the core side for better adhesion. When we start to create multi-gigabit SerDes networks, vendors began flipping the smoother drum side down, commonly called RTF or reverse treated foil. Over time, it became smoother, but rougher mud side still remained. And then industry created the smoother drum side. It was flipped back to the face to the prepreg side as copper manufacturers developed smoother matte side processes, VLP nodulization, and this became HVLP. There are different models, mathematical models to describe the copper roughness. Most popular one is these three: Hammerstad-Jensen, Hurray-Snowball, and Cannonball model. I will not be focusing on them here, but I will just leave it for the reference. So, the planner. It actually can manage, track, and model copper roughness and loss on both sides of copper foils. Inside the library, you can choose the copper roughness if it's available on the manufacturer. For example, in this case, we have 4 different options for this exact laminate. The planner also tracks and model roughness for plating and sequential lamination. In sequential lamination, take in consideration build-up layers. Usually it uses HT copper foils because they're rough and have good peel strengths. Default roughness set is to 8.5 microns. Plating has its own unique roughness, and research says that RZ around 3 microns is a good value if you do not have exact information. And there are some rules for prepreg side roughness. if the laminate manufacturer has given us a prepreg site roughness for specific fault grade, we use that. If we don't have that number, we use core site roughness for the prepreg. And if we don't have nothing, we use these generic but quite reasonable values. Detailed insertion loss modeling in zPlanner. zPlanner uses real materials with data from the laminate vendors. For example, this screen shows TU885 targeting PCI Express 5.0 and include DK&DF as a function of frequency and resin content. Copper false roughness modeled on both sides. Inside the zPlanner, you can right-click on dielectric and redesign the whole stackup to another material to simulate loss performance. You can explore copper roughness options and recalculate insertion loss. You can quickly export it to hyperlinks to sign-off and whole board simulation. And you can have faster and much less expensive than taking 6 months to build and measure signal integrity test vehicles and tens of thousands of dollars. I created some stackup just for demonstration purposes. It's pretty reasonable, it's pretty realistic. And let's have a look at this. What we can check using zPlanner from the real world. I already mentioned that we have two representations of stackup. It is specification stackup. This is how engineers are actually creating it and sending to the manufacturer. And there is fabrication stackup. Fabrication means that it taken in consideration the prepreg height thickening due to lamination process. There are many options that can affect your stackup in the result. Let's start from the vias, for example. Here I can go to edit via spans. And if you notice, I have a quite unreasonable structure. I have one through-hole via and several sequentially laminated vias. Physically, it is not possible. So normally the good tool will tell you about this. And if you turn on the option show via DFM errors and warnings, it will actually show you something like that. As you can see, we have an error here saying blind and buried vias should not have the same start and stop layer. And exact details about this problem. Mechanically drilled via span number 2 from second layer to 7 and via span number 8 from second layer to 8 have the same start and stop layer. Consider separating them with a prepreg for drill access or employing through-hole vias with front-back drilling. Another problem here is that buried vias is recommended to be resin filled, but we do not have this filling. So this also is noted, and I can just go here and make it resin filled, so this error is not shown anymore. Another thing is symmetry of the vias. It is quite too much to have this structure because our stackups can be just symmetrical. So 2G to 7G can be symmetrical. So let me just add it. And then we don't need other stuff. Also, this information includes plating, aspect ratio that was calculated, okay, let's apply these changes. Next thing, is percent of copper coverage. So what is it? Why it is important? You see, if you have low percent copper in your signal layer, during the lamination process, prepreg will be replacing the etched copper, and this will result in decreasing the height of the prepreg thickness layer. Practically, it means the less distance to the reference plane, and as a result, you will have less distance, you will have different impedance pardon. How to extract the exact information about percent of the copper? Well, in Expedition layout, you can generate it from the report window. Let me start my layout and I will show it to you. So this is a project I was working with. This is just demo. What we need to do is go to analysis and reports. And here we can press calculate metal area button. Then we can go to file viewer. Yeah, that's it. And we can import this file in our zPlanner. So the default values of copper that is used will be replaced with the real one. Right now I have manually entered percent copper, but default values is like that. So to import the file, you need to enable prepreg sequence from adjustments, manually entered, and import file here. It's located in PCB, log files, calc metal area. And if I press OK, it will change percent of copper to new parameters. And of course, automatically recalculate all affected parameters, including impedance profiles. Another thing is you can turn on this option, use sequential elimination for accurate representation. And also you can see there are two buttons, specification and fabrication. Let me disable fabrication. And if we take a look at impedance profiles, we will see that in specification it should be 42.5 ohms on the top layer or 50 depending on net. If I enable fabrication, first of all, it will change the thicknesses of prepregs. Second, it will recalculate our effective impedances. You also noted that I have DXF window on the bottom. As I said, we have pretty extensive set of DXF checks for stackup. These checks can be separated by severity level, error, or warning. And of course, they will be showing you ways how to fix it. For example, this is the old one that we need to add prepreg between VS spans. There is bad small separation between power and ground on layers 4 and 5. It's 76.2. This is like right on the border of our rule, and any other stuff. Here we also can enable and disable copper roughness and how it's affected. So in this project, all settings already turned on. So I will not be focusing too much on this. But what we can do to show the difference is to compare stackups. Right now I can compare it versus itself, specification versus fabrication. As you can see, originally designed stackup had 71.1 micron on the prepreg between layers 1 and 2. But after the taking in consideration the percent of copper, it will be really calculated to the real parameter, real value. Apparently, in the result, our thickness of prepregs will be significantly decreased. You can see it in the bottom screen that specification plated thickness is 1153 microns, but after the elimination it will be actually smaller. It's around 1096 microns. And it can affect our design. Imagine you took this as okay and sent this stackup to your fabricator. Fabricator took a look and sent something different, like change materials, change something else. So we can import the stackup. Actually, let's compare more. Let's import A. Here we will import layer stackup B. Automatically, the planner marks in red differences in proposed stackups, and we can think about this. Should it be changed? Should it be sent to produce as is? Is it good for you or not? After that, you can also include copper roughness effects. If you have another alternative, we can add more and compare it. Library. As I said, my favorite part of the planner is that it has massive, really massive library of materials from the main manufacturers in the world. Rogers. Let's click this quickly existing filter, and you can choose any material and see its information. In our stackup editor, we can find any analog and replace material to fit the new requirements. Right click on the material, swap material to Z0 library, and for example, let's say I want to use hook. As you can see, the whole stackup being recalculated. Construction automatically applied as well. Here you can see that it was recalculating impedance profiles on every layer for single-ended and differential layers, differential pairs, sorry. And if you're happy with the result at stackup, you can go and export it into Excel to share with your manufacturer. Do you have questions? Okay, as usual, you know my email. You can send your questions and requests to me directly, and see you on the next webinar. Thanks for attending, guys.